of mechanisms such as oxidation reduction potentials, redox reactions, group transfer radical production reactions. And we're going to look at those radicals because they're a little bit more problematic in biochemistry. We're equating back to Gibbs free energy in regards to the KEQ, and particularly understanding what we've come to terms with in regards to the delta G in its negative or in its positive form, negative being favorable reaction, which is exergonic, and positive being endergonic. And we're going to ideally then have that coupled to some other reaction energy-wise to give us a forward motion. We looked at the equilibrium constant in regards to the KEQ and Ka, and understanding again when delta G prime 0 is negative, 0, or positive, it gives us an opinion in regards to the KEQ and where that particular reaction is going to be moving at standard equilibrium constants and pressure. We gave an example of glucose 1-phosphate and its enzymatic transformation to glucose 6-phosphate and looking at the amount of energy that is released, in this case minus 7.3 kilojoules per mole. But if we were going to do the reverse reaction, we'd need the equal amount, again, conserving mass law energies in regards to thermodynamics. But it doesn't tell us anything about the reaction spontaneity. And so, again, we've got to think about that very carefully and put it into light. We were also talking about reactions in regards to, importantly, these half equations, where we see a generalized reaction in its full entirety, which is actually made up of a number of individual reactions, as we see here with the degradation of ATP and phosphate pyruvate moving to pyruvate and producing inorganic phosphate, and the various energies that we can actually obtain, but noting, again, the sum and reverse, depending which direction these particular reactions are going. In this case, we're going from ADP to produce ATP, therefore we need to reverse this reaction and change the signage of this particular reaction to positive because it's going to require energy to do that. And this particular reaction here, the phosphate pyruvate to inorganic phosphate, is going to actually fuel that particular reaction, giving it that negative 30.5 kilojoules that it requires, because remember this is going to be positive because it's in the opposite direction, and therefore giving us a total surplus energy of negative 31.4 kilojoules per mole. So that gives us an idea in regards to we can actually then use this energy elsewhere to fuel other coupled reactions that may not be moving forward given their particular energy barriers. And remember, we're simplifying and adding to our understanding that this is an enzymatic process, and that today we're going to look at ADP and ATP in regards to the overall reaction that these guys are going to be undertaking. So we got basically finished up before the spring break on this particular slide, which is basically a whole load of chemical reactions. We're actually going to examine most of these particular ones in regards to what they actually do, particularly today, these guys in regards to ATP and ATP hydrolysis. We're going to also look a little bit at the UDP glucose system in regards to the capacity to move this glucose to become a phosphorylated version, and also being able to produce glycogen, which we'll see in a few slides later. So let's have a look, importantly, at ATP. We've kind of, from our biology backgrounds, we've come to the understanding clearly that this is a energy-carrying molecule. It is the currency of all cells with a nucleotide ribosome sugar and basically 1, 2, 3 phosphate groups. These are actually attacked specifically through the hydrolysis, utilizing water as a molecular reactant on the first phosphate group, breaking this particular bond and giving this particular negative hydroxyl component and a negative oxygen in the resulting component, which is going to be then converted with a hydroxyl. So we're going to see basically the position of 2 hydroxyls with the 1 hydroxyl component and 1 hydrogen component adding to that particular oxygen, as we see here in the blue and in here with the product of the ADP coming from the ATP. So the hydrolysis of ATP is highly exergonic, and we get a lot of energy coming from that. But the interesting thing is we have to have this charge stabilization to occur to allow us basically a capacity to undergo further reactions with the ATP. So we get this phosphate stabilization by resonance structure, as we see here, and that gives us a capacity to start working with this particular molecule as a source of energy or a source of group transfer. And we'll see these later on. But ultimately, we're looking at this particular guy, the ADP minus 2, given it has 2 minus charge states there. In our ATP, we have 4 minus charge states there. So again, we're going to have to kind of think about this kinetic stabilization, particularly at physiological pH at 7, because we're going to have a sequential component to allow us to remove additional phosphate groups or add additional phosphate groups to give us the various energy currency carriers. And as we've already indicated and seen with cyclic AMP, that this particular constituent can be cyclized and have a different consequence in regards to just being an energy carrier, but actually being now a transmitter or a stimulant in biological processes. So again, let's continue with our hydrolyzation. And we've got the stabilized ADP, which has got the first phosphate group removed. Hydrogens come from water. And we know that through radio labeling. And I'm going to actually do a tutorial tomorrow morning on radio labeling, because we're going to utilize that in the homework and in the exam. The book doesn't really cover it too well, and so please come along and we'll make sure that you get abreast to what you need to understand about radio labeling and how you can use radio labels as a friendly element in biochemistry to track and trace certain materials. So once we get to this particular component, we're going to go through another ionizational process to get this deprotonation to occur, to allow us basically to have the reactive species. So we have a greater solvation of capacity and allowing us then to attack this particular guy to make then a MP if need be. Now, the whole thing in regards to the balanced equation, in regards to the negative charges, we're going to basically see a positive, 2 negatives, 3 negatives, and we're going to get a balanced equation in regards to the 4 negative charge state on the ATP to start off with. But with that particular system, when we see the hydrolysis with molecular water, we're going to be able to produce minus 30.5 kilojoules per mole. So we're going to have some hydrogens released, we're going to have some phosphate released, and then we're going to have the resulting ADP being present. But again, we don't normally put these negative charges in here, understanding that there's a resonance structural capacity and that we usually basically keep it pretty well neutral. But what we actually really see in biology and in chemistry and in biochemistry is stabilization using various ions. So again, these negative charge states to try and stabilize the three-dimensional structure of these guys to be ready for the next reaction. In this case, they use magnesium to be able to stabilize these particular structures. So again, we might see magnesium ADP, magnesium ATP, trying to ensure that we get a minimal charge state distribution. Now, there are other things that might also happen. So let's have a look at the situation with phosphate interacting as a molecule reagent to promote a reaction. And this happens with the hydrolysis of phosphoenol pyruvate, PEP, which we'll come back to a little later on. But ultimately, we see phosphoenol pyruvate as this particular molecule, and it has been phosphorylated by an enzyme. And what's going to happen, this phosphate group is going to be a great leaving group to cause a structural rearrangement in this position here. And what we're going to see is the movement of this particular double bond. So when water comes in, we're going to cause the hydrolysis, same situation where we'll see hydroxyl be split and a hydrogen be split of the water molecule, and basically provide you with the hydrogen here and the hydroxyl on the phosphate group, producing the inorganic phosphate. This will lead to a particular compound called pyruvate, and we'll study this guy shortly. And it has two forms. It has an enol and a keto form. And in this particular structure, it's not so stable. There is some presence of it. And it has to go through this particular situation to become a hydroxyl group to allow further reactivity. But in the tautomerizational component, this is the favored form, the keto form, in regards to having that double bond from that oxygen constituency and making this a single bond coming from the double bond in this position. Now, this time with phosphoenol pyruvate and with the hydrolysis utilizing molecular water as a reactant to produce pyruvate, we get a very large quantity of energy in minus 61.9 kilojoules per mole. And again, we also produce that inorganic phosphate, which is going to be taken up to produce phosphorylation activities or further ATP from ADP. So this particular reaction, through a hydrolysis reaction, produces a very favorable negative charge, delta G prime zero, and then has the capacity to feed other positive delta G reactions in this particular process. And we'll see this when we look at glycolysis today. Now, another molecule within the glycolytic pathway is the hydrolysis of 1,3-bisphosphoglycerate. This particular molecule also uses a situation of having a phosphate group attached to, in this case, the carbon number 1 position, and also has a phosphate group attached to carbon number 3. The issue gets down to there's selective processes with the enzyme reactivity to select this particular phosphate group over this phosphate group. And again, utilizing the same process, using molecular water as a hydrolysis reaction and splitting that water to the hydrogen and the hydroxyl position, we will see then basically the release of the inorganic phosphate. With that hydrolysis, we produce 3-phosphoglycerine or glyceric acid. And in this case, this little sugar has the capacity to have the carboxylic acid being present. But again, also we see this tautomerization, this resonance structural capacity, and a favorite form in the form of 3-phosphoglycerate. So we're going to see this guy being more talked about than this particular intermediate because of the ionization process and producing this resonance structure for stabilization. In this case, with 1,3-bisphosphoglycerate, to produce 3-phosphoglycerate and the various charge state capacities. Here we have 3 charge, 5 charge, so 5 negative plus 1 is 4. That's basically then cancelled out by the 1,3-bisphosphoglycerate. We see another delta G prime 0 in the negative state in regards to exergonic reaction, which is favorable to being negative 49.3 kilojoules per mole. So in this case, we see the importance of the phosphate group as well as the presence of molecular water driving this reaction forward. And it's going to be only through the ionization process of establishing these resonance structures to give us the next stage of being able to move that particular structure through to the next derivatization of this particular functional group. So we've come across then 2 reactions which utilize the binding of phosphate to a labile bond, the utilization of molecular water to hydrolyze that particular bond, and the splitting of that molecular water into a hydroxyl and a hydrogen form. And this is why radioisotopes become important, because we've been able to trace this particular behavior by using either P32, oxygen 18, tritium in sense of hydrogen, and oxygen 18. So again, we have the capacity to use those 3 radio-labeled isotopes to measure where those particular reactions are occurring and what's leaving and what's staying behind. Reactivity is very important in regards to it can't be created or destroyed, but it can only be accounted for and has to be accounted for in the whole entirety. So we'll talk more about that tomorrow. So another particular reaction which we're going to become very familiar with also produces a resonance structure is the acetyl-CoA. And we've already seen the structure of acetyl-CoA. And in this particular guy, it provides a ethyl ester, which provides you an enormous amount of energy. And we're going to see this particular reaction come back to us time and time again with the cleavage with molecular water, producing then coenzyme A. So here we have acetyl coenzyme A being present. We're going to remove the acetyl group in regards to the hydrolysis from this particular ethyl ester and get an enormous amount of energy from this. In this case, the byproduct is going to be acetic acid. So here we have acetic acid here. And acetic acid in this case is going to form a resonance structure through ionization to produce acetate, the acetate ion. And again, we can bring this whole equation into the hydrolysis of water with acetyl-CoA to give us the acetate, the coenzyme, and hydrogen ions and minus 31.4 kilojoules per mole. So again, this has this replacement situation where we've seen previously with the phosphate with the oxygen. We're basically kind of changing that to an ester bond and giving us a higher capacity of energy than we just see from a simple removal of phosphate. So again, the summary, these hydrolysis reactions that we're going to study are going to give us negative delta G. They are more stable due to their charge separation given their resonance structure and their bond breaking capacity. They're going to be a stable constituent more so and reactive constituent in an ionized situation, and their particular ionization to ensure their capacity is going to be adopted through a resonance structure. So we're going to see these resonance structures be produced to give us the reactivity and stabilization of the individual molecules and allowing them to actually interact with other forms. So when we have a look at our thiol ester versus oxygen, we can see the dramatic difference in regards to the delta-free energy capacity within these particular bonds. And in this case, we have the oxygen ester and the thiol ester. As you can see, the thiol ester gives enormous more energy than we would see with the phosphate or an oxygen ester. So a lot less energy from that oxygen ester. So this is why we're going to see the thiol ester becoming a very important player in regards to energy transfer and energy movement within the cell. So the other thing is we've got to make sure you understand that when we see ATP being involved in a reaction, it is not just leaving that phosphate group to react with the reaction. It actually participates and actually forms a covalent bond intermediate with that particular phosphate. So let's have a look at the energy transfer via what we call group transfer. And so it's not, we've illustrated a simple hydrolysis, but actually it's actually more complex. So we might actually write a first chemical reaction in regards to producing glutamate and glutamine, so two amino acids that are related to each other, and they're going to utilize, in this case, glutamate is going to use ammonia or a nitrogen source to basically put its position of nitrogen in this position here. It's going to require ATP to do that. So when we normally write the one-step reaction, we might utilize this with the nitrogen source, with the ATP, degrading to give you the energy to form ADP and PI, releasing that PI and that ADP, and in the process having that energy to sink in to change the bond rearrangement to give you this positioning here with that nitrogen source on that carbon branch of the glutamine to produce glutamine. And we're going to see this reaction time again also when we look at the urea cycle a little further on in this lecture series. But actually what happens is a two-step reaction. So I want you to be very clear when we see this, there are multiple steps occurring in these particular reactions. So here we have glutamate, and the first thing is we're going to prime the glutamate with the phosphate group and utilizing an enzyme, and we're going to consume ATP and produce ADP and present the phosphate group onto the carboxylic acid to give us that enzyme-bound component, very short-lived, very highly reactive, to give us this leaving group. And this leaving group is going to then present a chemical environment that is going to allow the lone pair of electrons on the nitrogen to attack this carbon constituent to give you then the glutamine component through the displacement and the leaving of the inorganic phosphate. So here we have our first reaction with the ATP being degraded by enzyme system and taking the substrate bound to an enzyme to give you an intermediate to allow it to have that phosphorylation to occur. And then that phosphorylation gives you the capacity as a leaving group to utilize those lone pair of electrons to attack that carbon group and present a bond in this form in producing glutamine. So ATP group transfer is a two-step process the addition first off of the phosphate group to the substrate, and then finally the displacement of the phosphate group or the phosphoryl group releasing inorganic phosphate and giving you that susceptibility to then cause a reaction at that leaving group site. So we're going to commonly see this throughout the rest of the semester. So I want you to kind of keep familiar that this is just not a simple approach. It's actually a more complex multi-step reaction than illustrated what we'll see commonly in these particular types of reactions. Now, the overall release of molecular energy might also be in small sequential steps. And they're going to be additive. Remember, we talked about the issue of the adding of the negative and the positive delta G's and changing the half equations if need be. So we might see an overall reaction giving us a particular value, which is going to be basically correct in regards to the degradation. So let's have a look. We're going to talk about fatty acid biosynthesis and fatty acid degradation, more so fatty acid degradation, in coming lectures. But I want you to understand first off, when we have a fatty acid and coenzyme, we're going to produce a fatty acid acyl coenzyme. And this is the guy that's basically going to be the intermediate with that high energy group to give us a thiol ester to allow us to do some work. So the idea is that we're going to have an endergonic reaction first off to get this guy going, which is going to be a problem. We're going to have to meet this energy requirement to allow this particular reaction to go forward. Now, we can do it partially by the issue of degrading ATP to ADP and producing pyrophosphate. Now, this is two particular constituents of phosphate, and we're going to have the capacity. Actually, that should be AMP, guys. That should be AMP, not ADP. Let me just change that. Okay, whoops. That should be AMP. Let me change it. Let me get out of there. Pretty sure that should be AMP. We can check that quite quickly by looking at this. So here's our yes, so here we are. We have ATP going to molecular water, AMP, and pyrophosphate. So not phosphate, but pyrophosphate. So containing two moieties of phosphate. And the point I'm trying to get to, this becomes a very substantial reaction, because here we have the full degradation of ATP to AMP, giving us minus 45 kilojoules per mole. So it's good, we're getting some energy. But we can take that pyrophosphate, those two moieties of the phosphine hydride bond, and still further cleave it to give us some more energy in the form of negative 19.2 kilojoules per mole. So we're looking at the full degradation of ATP, but we're doing it not in the normal sequential steps. So we could go from ATP to ADP to AMP. But we find it more preferential to go from ATP to AMP because of the cleavage bond, and we'll look at that in a second, and then take that pyrophosphate and further degrade that phosphate and hydride bond to give us the negative 19.2 kilojoules per mole. So in this case, what we see is then a summational event here. These are all in the negative, and we're going to be basically allowing us then to minus, this is a positive, and these are negative, and we're going to be basically negative 33.4 kilojoules ahead. So overall, this reaction is hexagonic. We're going to be ahead with the amount of energy that we produce. So this is going to be a negative sign. Let me put that in there just to make sure that you're fully aware of that. Okay, oops. So a negative sign, importantly, indicating clearly that we are ahead, that we have an hexagonic reaction. So we can see how important this AMP, ATP, ADP, and pyrophosphate or phosphate situation is going to be. So the overall release of energy might be in these little discrete steps in regards to the manipulation of the main energy source in the form of ATP to go through this capacity to have the acetyl-CoA come off to produce the thiol ester. And remember that thiol ester in its own right, if we cleave that thiol ester from the fatty acid, we're going to get a lot of energy also, and that's going to drive that reaction. But we're going to study more of this when we see beta oxidation in coming weeks. So let's have a look at the difference between these phosphate groups in regards to either hitting the ATP, AMP constituencies. So we've looked at phosphoenol pyruvate with that particular first removal of that phosphate group. We're going to get a fair amount of energy, around 31 kilojoules per mole. We get a little bit less energy with that phosphate group with the 1,3-bisphosphoglycerate, again, removing that particular component. But as you can see here, there is a boundary in regards to what we saw with glucose 6-phosphate or glucose 1-phosphate in regards to the amount of energy that is required. So this guy, ATP, is going to have the capacity to do various different works given the different requirements of these particular chemical functionalities and how they bond to phosphate. So we have high energy compounds, which are minus 25 kilojoules per mole, which are greater than 25 kilojoules per mole, and low energy compounds, which are less than 25 kilojoules per mole. So we're going to keep this in mind where we're going to try and couple these higher energy reactions and always be on top of having surplus energy available in regards to both promoting the lower energy reactions, but also being able to couple the summational energy surpluses to other biochemical systems, which will consume that energy and then therefore be able to then move them forward. So let's have a quick look at a few molecules here in regards to the energy release by hydrolysis for the phosphate bonds. And again, we're going to see all of these. We're going to study actually all of these particular guys in coming lectures in regards to most of these, except for phosphocreatinine, but all these other ones are actually a part of the glycolytic pathway. And as you can see here, the inorganic phosphate or the pyrophosphate, the PPI, going to two inorganic phosphate molecules, giving us that minus 19.2 kilojoules per mole, which gives us the capacity to move from ATP to AMP, which is negative 45 kilojoules per mole, and then take that pyrophosphate again and bring it down to here to produce two moieties of inorganic phosphate at that negative point, at negative 19.2. So again, discretional release of energy to the lowest entropy and entropy components in the Gibbs free energy to give us the capacity to suck out every piece of energy we possibly can in the most easiest route and function to get these molecules basically squeezed of their energy to drive other chemical reactions that are going to consume that energy. Now, ATP, we're focusing a little bit on today because it does also some other interesting things. So ATP, and we'll see this when we look at the TCA cycle, is that ATP has this capacity to move a position phosphate from one nucleoside to another, okay? So we know that ATP is essential in the formation of the individual nucleotides, A, T, G, and C, to produce the genetic code, whether it be messenger RNA or DNA. We also know ATP provides us an active transport in regards to consuming that energy and causing a phosphorylational functional change like we saw with calmodulin and some of the other transmembrane proteins to give you that structural change to then move molecules through, sometimes against a chemical electrical gradient. We also see ATP when we look back at our very first part of the lectures with the actin-myosin interactions, that we have the capacity to use ATP in muscle contraction. So I'm trying to illustrate here the ATP molecule plays an enormous role, not just as an energy carrier or a powerhouse or a power currency of the cell, but plays very integral roles in metabolism and processes, a bit like what we talked about with molecular water. Now, one interesting thing with this transfer of phosphate groups, we can transfer a phosphate group from one molecule to another, given the capacity of using enzymes. So here we have an illustration of ATP in its three phosphate constituents degrading to become ADP, losing one of these particular phosphate groups. These phosphate groups are transferred to an enzyme through a phosphorylation of a histidine. Without phosphorylation of that histidine, we then have the capacity to transfer that phosphate group to another nucleotide. Nucleoside. So basically, this is why you might see NTP and NDP. N just indicates that it's a nucleoside. And again, we're going to see this transfer. So we're always going to be able to take any of the nucleosides and be able to always come back to producing ATP by this group transfer. So whether it be GTP, CTP, we can always transfer that one of those phosphate groups, if it's fully loaded in its triphosphorylated form, we can always move that particular phosphate group back to adenosine and produce ATP. We may not be able to utilize GTP as a direct energy source. We might need to transfer it as ATP. So again, keep that in mind with some of the reactions we're going to see in the future, particularly when we look at the Krebs cycle. We also see ATP being an interesting phosphorylational donor. And we see this through what they call an SN2 nucleophilic displacement reaction. So you might want to reflect back on your chemistry, how that particular mechanism occurs. We know this occurs specifically given that we use radio-labeled heavy oxygen, oxygen 18, and we illustrate importantly that it is a phosphate 3-oxygen transfer, not a 4-oxygen transfer from the degradation of the ATP. And I'll show you this in the second slide in a second. So when we look at the attack on ATP, the primary attack is first on the gamma position of the phosphate chain of the three phosphate groups, then the beta chain to give you the pyrophosphate. So again, we have two positions in regards to that capacity. The nucleophilic attack at the alpha position then allows us to remove the whole nucleoside group and allow that to be transferred. And that happens also in some reactions and giving us then the three components of phosphate. So let's have a look specifically at this degradational process. So here we have our structure of our ATP, and we see alpha, beta, and gamma being the nomenclature for the individual phosphate positions. When we look at a group transfer using the phospho group where we have molecular water or an R, we'll put an R, heavy water or heavy oxygen constituent attacking this particular component, we're going to see a breakage occurring here. And in this case, at the gamma subunit, we're going to see 31.0 kilojoules per mole being released. When we see that particular attack in this position, get my pen back up here, in this position, we're going to produce this molecule. And we know we produce this molecule again because of the radio-labeled molecular water. So we're going to produce ADP, which is the resulting component, and one of these particular phosphol-containing groups. If we attack the beta position in regards to this particular guy, we're going to produce AMP and the phosphoanhydride 2 moieties of phosphate, so the phosphoanhydride bond as we illustrate here, and we see again the same displacement with that molecular water or that particular heavy oxygen positioning being in this particular component. Now this particular guy is going to then ultimately give us AMP and the pyrophosphate, which we can then further degrade to give us some more energy, and we'll find then basically we'll be putting the radio-labeled position in this position here. If we attack the alpha position of the phosphate group again with a radio-labeled oxygen and attack this position, we're going to remove, in this case, the pyrophosphate and still produce the radio-labeled constituent in regards to having this position being basically attacked with that radio-labeled constituent producing the adenyl transfer group, and this pyrophosphate component. So what I'm trying to illustrate here is the sequential breakdown of the individual molecules in regards to the different attacks on the alpha, beta, and gamma phosphate groups of ATP. And remember, when we get this guy here, which is this guy here, this pyrophosphate, this is pyrophosphate here, it's pyrophosphate here, but in its unlabeled form, we're going to degrade this further and produce negative 19.2 kilojoules per mole to produce this molecule here. So again, it's just an illustration in different aspects in regards to attacking these different phosphate positions. In this case, we can access various energies sequentially or all in one go, or allow us to make a choice when we want to further degrade, in this case PPI, the pyrophosphate, to give us that particular additional energy boost. So again, just an illustration of different cleavages within the phosphate group of ATP to give us different energies and different products, going from AMP to ADP, not in that particular order though, but usually go ATP, ADP, AMP. But as you can now notice and understand, we can go from ATP directly to AMP, producing the pyrophosphate, getting energy from that first reaction, further degrading the pyrophosphate and giving us more energy. So again, we have these capacities to mix and match the type of degradation we want to see with our ATP. Now, this is always a bit of a problem with students. They don't like this type of stuff with the electron flow, the redox oxidation reactions. But again, we're going to have to study these because these are very important reactions in regards to what's going to occur when we start moving electrons around. The electrons are going to be very important for us to move around and to be able to move them safely to allow us to generate a electropotential difference and a chemical carrier. So the flow of electrons in a biological circuitry can be moved by these types of molecules. We're going to talk about these ADP, ADH, ADPH, and FADH2. But in their electron carrying forms, they release the hydrogens and they become NAD plus, NADP plus, and FAD. So we're going to have these particular guys come back to us time and time again, and we'll talk a little about these guys also in regards to what they actually do and what they look like in a second. But ultimately, we're going to have to think about these reduction reactions and oxidation reduction reactions because they must occur together. We must always have a safe occurrence of movement of electrons from one system to another. So here we have a very simple reaction occurring with Fe2 plus and copper 2 plus, transferring the capacity to Fe3 plus at the cost of the copper 1 plus. So again, we have this reversible reaction in regards to what's occurring, but let's see what's happening in regards to the basic breakdown of these half reactions. The half reaction is telling us that Fe2 plus, when we remove a single electron, is going to go to, when we add a single electron, Fe2 plus, and we're going to go to Fe3 plus an electron. So that's the capacity. By adding this electron here, we're going to change the electron state of the ion. When we look at the copper component, when we add an electron here to the Cu2 plus the copper, we're going to go to Cu plus 1. So in this case, we need to identify the donating molecule and the accepting molecule. And this donating molecule, here we have the ion Fe2 going to Fe3 plus with that electron. That electron is then going to sink into the copper 2 plus to give us copper 1 plus. So the electron donating molecule is the reducing agent. The electron accepting molecule is the oxidating agent. And as they are combined as a pair, because they must occur both together, they are called the conjugate redox oxidation pair. So we're going to see this occurring not so much with these types of molecules, but with this type of molecule in the form of NAD+. So here we have oxidation, which is equal to a loss of electrons. Then that's going to be through the addition of an oxygen due to a loss of a hydrogen. So here we have NAD+, with a hydrogen and 2 electrons. It has a capacity to carry 2 electrons in an aromatic ring to give us NADH. This is the oxidized substrate. This particular reaction, which we'll see time and time again, is an oxidational reductase enzyme. In this case, we call it a dehydrogenase. So from the word dehydrogenase, we know it's an enzyme. It's causing a dehydrogen removal. So in this case, a dehydrogenase. So again, we have NAD plus with hydrogen plus with 2 electrons to give us this neutral molecule in the form of NADH. And we're going to come back to these guys time and time again. So again, NAD plus, NADP plus, and FAD as electron carriers, which will carefully and safely carry the electrons that we will put in these oxidation reduction reactions and move them to other reactions that we're going to utilize those electrons as well as their electromotive force, as well as the energy they carry to provide that coupled reaction. Now we have different types of reductional capacities in our molecules. So a more oxidized compound has more oxygen and less hydrogen. So we get these particular types of electron orbital diagrams, such as methane, in regards to having this capacity to have carbon with 4 bonds and sharing that with 4 hydrogens and those particular electrons. So the highest, Richmond or high Richmond in hydrogen gives us this more reduced capacity. But when we start moving to the more formal molecules that we're going to work with, like acetic acid, carbon dioxide, we're going to see the capacity of this changing in regards to the number of hydrogens and the number of oxygens around in regards to sharing those electrons. So you can see with these alkene, acetylene, formaldehyde, they have a fairly high reduced capacity compared to that what we see in a biological system which has a mixture of both hydrogen and carbon moieties. So how do we actually measure these types of potentials and the electron transfer and movement? We can do quite easily electrical chemical measurements. And this is a hydrogen electrode. So basically it's providing us a simple reference to what we should be seeing in atmospheric pressure and an equilibrium of protons and an equilibrium at a concentration of 1 mole of protons. So in this case, we have a reference point because we need to have a reference to say, okay, is this going to be a positive or a negative electrical potential difference in regards to a reference point. And we do that by looking at a proton plus 1 single electron to give us half a hydrogen. And this is what we call our reference point at 0.00 volts. So we do this by utilizing a hydrogen gas and a salt bridge to give us an electrical potential reference in regards to a reference cell. And in this case, we might contain a new solution in here, which is a concentration of an oxidizing reducing species. And we're going to see the reference change in regards to whether it be a positive or negative component in regards to the electromotive force. So again, the amount of electrons that have been circulating around the system. So by making those types of measurements, we can kind of understand what type of oxidation reduction potential that particular reagents have in this particular system. So when we look at these, we can use the Nernst equation, which is quite an easy equation to think about in regards to what's occurring with our system. So we have the number of electrons being transferred and moved, which is very important. We have the reduction potential of the species, and then also the reduction potential of the standard, which is the standard energy. The prime 0 indicates standard. But then we have the E value in particular in regards to the overall Nernst value, which is the reduction potential of both the oxidized reduced species together. And then we have Faraday's constant, which is a component in regards to a measurement of voltage. So standard electron motive force can be used to then calculate delta G. And this is where we're getting at. By making that electrical measurement, we can recreate that particular value in the form of free energy, and we'll show you that in a second. And that is given by the negative n of the Faraday constant by the change in the standard free energy that is present in that particular redox oxidation potential, giving us then the delta G prime zero. So let's have a basic look at one particular reaction in regards to acetaldehyde with our particular carrier and with a supply of electrons. This guy is going to do something in regards to providing some protons and some electrons and allowing us to have a reaction to move forward to change this molecule to produce ethanol and cause its release as a resulting reduced potential of NAD+. So let's have a look. We have two half equations to think about in this particular case. And then we have the acetaldehyde plus 2 protons plus 2 electrons to give us the capacity to give us ethanol. That's all well and good, but we need to have a source of these electrons and a source of these particular protons. We can measure the electrical potential of this particular reaction to be negative 0.197 volts. From our second reaction, our second half reaction, which is the degradation, or is actually the production of NADH, is we're going to take 2 electrons, 2 protons, and NAD plus to produce NADH plus 1 particular proton. Now, noting again the order at this particular reaction, this is what we've measured, but this is not what we represent in our reaction. Therefore, we must change again the value that we see in this particular guide, because this is going to be on the right hand side, on the left hand side, compared to what it's being presented on the right hand side presently. So in this case, we have negative 0.3 volts. As you can see, a very number of asterisks to indicate that there needs to be a signal change or a voltage change on this guide because of the order of the half equation. So we have the donor recognized in regards to the electron source. So this guy, we have those 2 electrons there. We need to be able to produce those guys and to produce the ethanol at the cost of the NADH, which is on this side. So again, we're going to change that particular sign to give us positive 0.32 volts, because it's the acceptor. When we add those two together, we now have a positive 0.123 volts in regards to this standard free energy of the electron acceptor donor reaction. So we've got the situation where we have our donor and our acceptor recognized. We have the voltage change. We have to then substitute a voltage change with the one particular reaction, because the half equation is not in the right order, to give us the overall voltage. Once we have that overall voltage, we can then use the Ernst equation and work out, importantly, what the delta G for that particular reaction is. In this case, we can look at the delta G prime 0 equals negative n, which is the number of electrons that are transferred or moved, which is going to be 2. And we're going to then use the Faraday constant, and then the change in the delta E prime 0, the electron transfer and donor voltage of overall measurement in that particular reaction. So here we have negative 2 times Faraday's constant times 0.123 volts, which will give us negative 30.7 kilojoules per mole, indicating that this reaction, if we have the aldehyde, acetic aldehyde, NADH, and a source of electrons, and the enzymes appropriate to transfer those through safely to produce ethanol and NAD+. And it's going to be a energetically favorable reaction, exothermic, hexagonic, and giving us minus 23.7 kilojoules per mole. If we're going in the opposite direction, so we're changing this arrow, we're going to degrade ethanol and have a source of NAD+, we're going to have to change then this particular equation and our half equations. And note, importantly, we're going to be going into a different direction. So we could have ethanol plus NAD plus going to acetic aldehyde, NADH plus hydrogens. So this time we're going to have this on the left-hand side. So we're not going to change this sign, but we're going to change this sign. So I think you need to be able to manipulate those. Some of those will be in the homework, and there'll be most probably something very similar on the exam, utilizing these half equations and being able to understand when you need to change the sign in the bioenergetic process. So when we see this whole reaction occur in regards to the degradation of glucose, you can see and understand we have 6 carbon moieties present in the form of glucose. There is oxygen, highly abundant, so there's a high capacity to have energy release. And as you can see, when we actually go through the full degradation of glucose, we can get a delta G prime 0 from glucose to completely carbon dioxide and molecular water to being negative 2,840 kilojoules per mole. So that gives us an enormous amount of energy capacity, but this is not going to happen by itself. It needs to be regulated by the various enzymes and the multitude of individual steps that we're going to examine to allow these electrons to be transferred by various coenzymes, various systems, to allow those electrons to be utilized and their reactive capacity to be utilized in reactions that are not going to be sustainable because of their delta G prime 0 requirement. And we're going to do this by utilizing these electron carriers. We've already introduced NAD+, but another equivalent is NADP+, and these are nucleotides. And basically, this is a nicotinamide adenine dinucleotide or a nicotinamide adenine dinucleotide phosphate, the NADP+. We have flavin nucleotides, and again, we're not see so much in the flavin mononucleotide, but we see a lot in the flavin adenine nucleotide, in this particular form in the FAD, and the FADH2, which is going to be carrying two electrons and two protons. And we're going to see this commonly occur in beta oxidation on fatty acids in the future, as well as seeing this occur also in the TCA cycle. And we're going to become more familiar with these particular guys shortly in what they actually do. So let's have a look at NAD plus, or NAD first off. So here we have the structure of NAD plus in its oxidized state. We have adenine, the nucleotide or nucleoside. We have the carbohydrate being present. We have the phosphate and hydride bond, two phosphate groups, and another carbohydrate with the nicotinamide group being present. So again, nicotinamide group, adenine nucleotide, two ribose sugars, and a pyrophosphate, which make up NAD+. Now, in this particular guy, we have this position here, which would be phosphorylated if this is the NADP+. Now, this does play some role in some of the reactions, but most of the electron capacity and carrying capacity is with this nicotinamide group. And it's this particular position here, the one in the red, is the nicotinamide group, that is going to play that role to carry those two electrons carefully, as well as those two protons. Or one proton, and release one proton as a free proton. So here we have two electrons coming into this aromatic ring with two protons coinciding. We're going to see one particular proton being joined to the aromatic ring, but causing then basically the situation of having those two electrons sunk into that particular aromatic ring, changing the positive charge to a lone pair electron and changing the double bond distribution of the aromatic ring, given that hydrogen constituents. Now, we know for a fact, again by using radio labels, that we could get the different orientation of where that hydrogen is going, either on the left or the right-hand side of this aromatic ring, or we call the A or the B side. This is now NADH in its reduced form because it's carrying those electrons and one of those protons. And we see the remaining proton being here in regards to the release. Now, we know things are going on in regards to the change of the pi electrons in the aromatic ring, given that we can look at the wavelength constituency of the two molecules in its oxidized or in its reduced state. So we can actually basically monitor the production of NADH at the expense of NAD plus, because in the NAD plus, the oxidized form, we're not going to see an absorbance in the maximum lambda of 340 nanometers compared to what we see with the reduced form. Because of those lone pair electrons, we have the capacity to have a greater absorbance in those particular field. But we do see a little bit of a decrease in the reduced NADH around 260 nanometers. But again, it's not as apparent as we see with that reduction and that increase in the reduced NADH in regards to the increased wavelength at 340 nanometers. So we can experimentally visualize what's occurring with these particular reactions. So let's keep moving forward in regards to what we see with some of these other electron transfer carriers. So NADH and NADP are formed or derivatized from niacin, which is vitamin B3. So if you think about your various foods you intake, look on the ingredients, because you will find a lot of these, particularly breakfast cereals, are actually fortified with niacin or vitamin B3 because of this particular issue in regards to having this as a part of the dietary intake to produce NAD and NADP electron carriers. It's very hard for us to actually produce niacin. So niacin or nicotinic acid is not an active form of nicotine. So smoking is not a capacity to provide you the appropriate niacin. Nicotinamide is another constituent that is very similar with that carboxylic acid, now with a nitric constituent. But also tryptophan can be metabolized to give you niacin, but it's a very, very poor source. So we're going to have this substituted into our diets with fortification or from natural foods that we consume in a balanced diet. Now, there is a problem. This is a very uncommon disease now because we have a lot of fortification in regards to your breakfast cereals and other foods that have this particular compound in them. Pellagra basically is a medical condition when niacin is a apparent deficiency in the body. As I said, we can get a small amount from the metabolism of tryptophan and allow us ultimately to actually get some. But what happens when we don't get enough tryptophan, or we cannot metabolize our tryptophan, or we don't get enough in our diet? We get some various medical situations. It's called the 3Ds: dermatitis, diarrhea, and dementia. Now, in humans, one of the first conditions is this black tongue. You can see it also in smokers, interestingly, and in dogs, they get this particular black tongue, which you can actually scrape off. And basically, also the dermatological components in regards to this kind of flaky skin, as well as these type of ulcerations on the skin. And you can see this photo is mostly from the 1890s. As I said, most of our situation in regards to most of this in regards to the disease state can be cured by the supplement with tryptophan in the diet. So a high level of tryptophan in the diet might be able to push over the niacin production, because you might not have the capacity to actually absorb the niacin itself. This is seen in alcoholics, where basically low intestinal absorption is due to basically competition in regards to the consumption of alcohol. Now, the interesting thing is you can live on beer alone if you have vitamin B3. So you can sustain yourself becoming a total alcoholic if you desire with caloric intake by distilled spirits or by alcohol, beer, but as long as you get B3 supplemented into your diet. And hopefully that would not be a consideration for you guys. But it's just an illustration in regards to some of these metabolic disorders or diseases we see due to deficiencies of certain elements or minerals or cofactors. And as I said, we very rarely see them now, given the way we understand diets. Dietary understanding is only a real newish science, only about 80 to 90 years old in regards to understanding the various vitamins, minerals, and supplements that one needs to keep a healthy body. So again, the research is still pretty newish. So the flavin nucleotides, these are from riboflavin, and you might also see this on your Frosted Wheaties ingredients on the back of your cereals. These are basically catalysts of oxidation reactions, and they use this flavin mononucleotide, or FMN, or a FDN, or FAD, flavin adenine dinucleotide, to do its particular job. The flavin nucleotides that we're seeing very similar with the heme group is a prosthetic group. So again, we have the carrying capacity of these flavoproteins to do their work, utilizing the flavin nucleotides as a prosthetic group. So they're not floating around freely in circulation. The interesting thing about these particular guys, they can actually be involved with more diverse reactions because they actually carry one or two electron transfers through the process than what we see with the NADH or NADPH, which only carries one electron through the system. So we have this capacity, two electrons through the system. We have this capacity to see then a difference in regards to their reactivity and the capacity of a reduction potential movement. We can also see their change in their pi electrons in the aromaticity of the compound, as we've seen with the NAD plus in regards to the NAD plus and NADH in the reduced state, going to change that 340 nanometer range. We have a lot of these flavin nucleotides present in these various light receptors, particularly for plant growth, and also some of these systems for DNA repair, because of their electron capacity either to carry or provide or sink electrons in. They become very important in trying to maintain electron homeostasis. And we're going to talk about that when we look about free radicals. So here is the molecule here. Here we have the adenine group, the carbohydrate, two phosphate groups, and then another carbohydrate linked to a very complex three-membered ring called an isoanizoline ring. This guy has a capacity to utilize this central positioning to change the pi electron capacity by absorbing one electron at a time. So we have a semiquinone and a fully reduced form. So again, these guys have the capacity to give us this electron transport system, which will carry these electrons safely throughout the system with particular proton presence also. So here we have our first one, FAD, coming in with one electron, and then having FAD going on to become FADH, and then an additional electron coming in to produce the FADH2. And these are the ones we're actually going to be more focusing on than the FMNH2. So we're going to be more looking at this guy, the FADH2, the fully reduced versus the semiquinone and the fully oxidized version without any electrons here. So the important thing that we need to bring into concept is that this is a temporary transfer or holding of electrons, and it's that particular transfer and that capacity to release those electrons that give these molecules such an important role in our metabolic pathways. So we're going to see these guys have their capacity to bind and associate with other proteins, which may also regulate, control their transfer of those electrons, as we'll see in coming lectures. So I want you to just be familiar with some of the terminology that we've talked about today, understand the concepts of free energy and energy transfer, recap the bioenergetics that we understand, the relationship between KQ and delta G prime zero, the relationship between delta G and delta G prime zero also, and additive reactions. The issue about the ATP hydrolysis and how we can hydrolyze certain aspects to produce different moieties, which will give us energy later on, such as the pyrophosphate, and then group transfers, and then also the Nernst equation, as well as the electron carriers. These are all very important. So we've now finished our particular first part of our real system. We are going to now look at the metabolic pathways, which then will basically provide us the capacity to look at